Hi, my name is Reagan Wakefield, and this is my Physics 2211 Black Hole Lab. This lab has two parts. The first part is to simulate a system with a black hole and a star to find the mass of the black hole. The second part is to determine an initial velocity such that you can fly a spaceship close to the black hole without crashing into it or an orbiting planet, and then escape away from the black hole. We will do this by constructing two computational models using GlowScript. The first fundamental physics principle used in this lab is Newton's second law, also known as the momentum principle, which states that the rate of change of a particle's momentum is given by the force acting on the particle. The second principle is Newton's universal law of gravitation, which states that any particle attracts any other with force proportional to the product of the masses and inversely proportional to the square of the distance between them. The first formula we will use is the momentum principle. F net equals the change in momentum over the change in time. Since we know this, we can substitute in dp over dt everywhere it says F net. We'll also use the net force is equal to F net parallel plus F net perpendicular. We can break this down even more into individual formulas for F net parallel and F net perpendicular components. We'll also use the position and velocity update formulas, which use initial conditions to predict the future position and velocity of an object. In addition, we'll use the formulas for gravitational force, which equals the gravitational constant g multiplied by the mass of the first object and the mass of the second object divided by the squared distance between them multiplied by direction. For part one, the system is the black hole and the surroundings are the star and all other forces. For part two, the system is the spaceship and the surroundings are the black hole, planet, and all other forces. As we will see later on in the presentation, my unique black hole mass equals 2.21 times 10 to the 34 kilograms, and my initial velocity for the spaceship will equal negative 4.9 times 10 to the power of 7 in the x direction, and 2.3 times 10 to the power of 6 in the y direction. Here are the initial conditions for part one. I entered my email to generate a unique star trajectory. The gravitational constant, the mass of the star, and delta t, and the number of seconds in a day were all given. In this while loop, initial and final velocities are pulled from the x-val and y-val lists. I found the initial and final momentums by multiplying the mass of the star times the initial and final velocities. I used these initial and final velocity and momentum calculations to find delta v and delta p. I then found dp dt by dividing delta p by delta t. With the knowledge that a derived version of the momentum principle is dp dt, we can set dp dt to equal F net. I then calculated dp dt parallel, which we then set equal to F net parallel. I did the same thing for the perpendicular components. Finally, to find the mass of the black hole, we used the force of gravity equation. The last part of my code helped visualize the arrows to represent the forces. My calculations resulted in an F net equal to approximately 1.03 times 10 to the power of 29, and F net parallel equal to approximately 4.55 times 10 to the power of 27, and an F net perpendicular equal to approximately 1.03 times 10 to the power of 29. In addition, my unique black hole mass equaled 2.21 times 10 to the power of 34 kilograms. Here are the initial conditions for part two. I began by inputting the black hole mass that I found from part one. The gravitational constant, planet mass, and ship mass were all given. I then found the initial velocity in the x and y direction such that the spaceship would get close to the black hole but not crash into it. The initial velocity I found in the x direction was negative 4.9 times 10 to the power of 7, and the initial velocity I found in the y direction was equal to 2.3 times 10 to the power of 6. I found these values through trial and error. Within a while loop, I found the force of gravity on the planet by the black hole and the force of gravity on the planet by the spaceship by using the force of gravity equation. I then added these two forces together to find the net force on the planet. I repeated these steps to find the force of gravity on the spaceship by the black hole, the force of gravity on the spaceship by the planet, and the net force on the spaceship. I then used Newton's second law and the position update formula to update the position and velocity of the planet and the ship. Here is a video of the code in action. The planet is in blue and it is orbiting in a circle. The spaceship is in magenta, and as you can see, it gets very close to the black hole, but does not crash into it. The spaceship then exits away from the black hole. The first discussion question asks how the net force and its perpendicular and parallel components differ from the rate of change of momentum and its perpendicular and parallel components. Mathematically, there's no difference. The main difference for this lab, however, is the rate of change of momentum is something we can calculate through observing the object's position and momentum. On the other hand, the net force is not something we can calculate without knowing the mass of the black hole. The second question asks what the initial velocity would have to be if you wanted the spaceship to orbit around the black hole. This question was difficult for me to answer, but the image you see is the closest I got. Through trial and error, I found that the initial velocity would be -9 times 10 to the power of 5 in the x direction and 1.5 times 10 to the power of 7 in the y direction in order to get this result. Finally, some sources of error within this lab are human error due to closed script. Specifically, there could have been errors while using trial and error to find the initial velocity in part 2 of the lab. Thank you for watching.